NASA's Mars rovers have been transmitting massive amounts of data, terabytes worth, back to Earth for years. Yet within this mountain of information, no one had detected certain subtle but consistent patterns until Grok 3, an advanced artificial intelligence developed by XAI, was deployed to analyze the raw telemetry streams. Grok 3's advanced pattern recognition capabilities uncovered data correlations that significantly altered scientists' understanding of Mars. These were not just unusual readings or anomalies often dismissed. They represented real scientific findings hidden in plain sight within vast, overlooked datasets. Over the past decade, NASA has collected an unprecedented volume of telemetry data from its various Mars missions. Curiosity alone, since landing in 2012, has returned more than 1.88 petabytes of raw sensor data, including images, radiation readings, and environmental measurements. Combined with data from Perseverance, Spirit, and Opportunity, the total archive exceeds 12 petabytes, equivalent to around 240,000 standard Blu-ray discs. The overwhelming scale of this information made it infeasible for human scientists to examine every aspect in detail. Grok 3 was developed to address this very challenge. Unlike earlier AI systems, which typically focused on single data streams in isolation, Grok 3 was capable of multimodal analysis, examining correlations across various types of data simultaneously. It connected visual imagery, radiation measurements, seismic data, atmospheric readings, and even minor fluctuations in rover performance, which had previously only been used for mechanical diagnostics. This capability allowed Grok 3 to see what human researchers and traditional systems missed. The collaboration between XAI and NASA's Jet Propulsion Laboratory began as a test of advanced AI in scientific data interpretation. No one expected it would lead to findings that would challenge long-standing assumptions about Mars. Mars rovers are outfitted with complex sensor arrays designed to capture everything from radiation and atmospheric conditions to detailed geological imagery. Each day, these machines send back between 100 and 250 megabytes of raw data. Over time, this accumulated into a veritable scientific archive. Historically, scientists divided this data by specialty. Geologists focused on rock formations, atmospheric, experts on climate data, and so on. Even earlier AI tools mirrored this compartmentalized approach. Grok 3, however, adopted a fundamentally different method called cross-modal pattern recognition, which examined how diverse datasets correlated with one another over time and location. What Grok 3 uncovered was far beyond expectations. It discovered radiation patterns in Curiosity's data that had long been dismissed as random noise or instrument error. These readings came from the RAD instrument and had been filtered out by NASA's software due to their inconsistency with known radiation phenomena. But Grok 3 found these anomalies weren't random. They repeatedly occurred in specific geological contexts and were linked with subtle shifts in mineral composition, detected by spectrometers on board. Even more surprising, when Grok 3 cross-referenced this with data from other missions, specifically Perseverance in Jezero Crater, it identified similar radiation signatures. These matching readings occurred in locations more than 3,700 kilometers apart. The consistency across missions and instruments became impossible to ignore. When the findings were presented to Dr. Sarah Chen, NASA's planetary science director, she was initially skeptical. In a recent interview, she noted that her first reaction was to assume the AI had made an error. The patterns contradicted the known understanding of Mars' subsurface and radiation behavior. She assembled a team of radiation specialists and geophysicists to investigate. After 3 months of independent analysis, the team reached a remarkable conclusion. Grok 3's findings were valid. What had previously been written off as statistical noise turned out to be a repeating pattern embedded in the geology of Mars. What Made this discovery so compelling was that it wasn't isolated to a single site. The same patterns were present across widely dispersed regions of the Martian surface. After verifying the radiation anomalies, NASA teams began mapping the signatures against the planet's known geological features. The results were astonishing. The radiation anomalies aligned with what appeared to be subsurface structures possessing highly unusual electromagnetic characteristics. These structures, located approximately 20 to 40 meters beneath the Martian surface, seemed to form interconnected paths stretching for hundreds of kilometers. Their composition was especially perplexing. They absorbed and redirected cosmic radiation in ways that didn't correspond with any known geological material, whether on Mars or Earth. Initial theories proposed ancient lava tubes or dried water channels, but their electromagnetic behavior didn't align with known rock or sediment properties. More astonishingly, these formations demonstrated an unexpected ability to conduct electricity, almost functioning like a subterranean network of natural wiring. When the data was mapped globally, researchers discovered that the structures formed geometric patterns with surprising regularity, radiating outward from central points. Scientists began referring to this arrangement as the Mars grid. What stood out most was that these formations didn't conform to typical geological formations such as crater rims or tectonic fault lines. Moreover, they appeared undisturbed by meteor impacts or surface erosion, which implies either exceptional durability or the possibility of some form of preservation or even maintenance. Due to the significance of these findings, NASA assembled a multidisciplinary team including geologists, engineers, physicists, and astrobiologists to study the implications. One of the most difficult aspects to explain was the geometric consistency of these underground formations. They often intersected at precise 120-degree angles and maintained regular spacing across vast areas. Dr. Chen's team concluded that the probability of such regularity occurring naturally was extremely low. They examined every plausible geological process, from tectonic to crystalline formations, but none accounted for the scale and precision of the observed patterns. To rule out errors, NASA reprogrammed the Curiosity and Perseverance rovers to perform targeted measurements in regions where Grok 3 predicted these structures would be located. The rovers conducted readings every 10 meters, using ground-penetrating radar and enhanced radiation detectors. The results confirmed Grok 3's predictions with over 97% accuracy. One of the most revealing moments came when Perseverance drilled into an area above one of the identified structures. The extracted sample showed a unique composition of electrically conductive minerals, including magnetite, hematite, and an unknown form of silicate with high conductivity. Dr. James Wong, a geophysicist from MIT not originally involved in the project, called the discovery potentially the most significant since confirming ancient water on Mars. This discovery progressed rapidly, from Grok 3's initial pattern detection to full scientific validation in less than a year, which is remarkably fast by scientific standards. Each stage of investigation only strengthened the findings, leading NASA to prioritize further exploration of these subsurface features. The agency has already begun redirecting rover missions to areas where the structures come closest to the surface. There is ongoing debate in the scientific community about what exactly these formations represent. Some believe they are the result of geological processes that remain unknown, while others entertain more speculative theories. Regardless, all agree that this represents a paradigm shift in how we understand Mars. At the heart of this discovery was Grok 3's unique AI architecture. Its neural network was designed for multimodal, context-aware analysis. Rather than examining one type of measurement at a time, it correlated data across dimensions. Radiation readings, mineral content, geological context, time of day, and even seasonal changes. Its unsupervised learning algorithm flagged correlations with a probability of occurrence below 0.001%, filtering out nearly all false positives. NASA then applied a three-phase validation method. First, it reanalyzed the raw data using traditional tools, but with Grok 3's flagged patterns in mind. Second, targeted measurements were taken with recalibrated rover instruments. Finally, older mission data from Spirit and Opportunity was reviewed for overlooked signs of the same patterns. Several natural explanations were proposed, such as magnetized mineral deposits from ancient groundwater flow, or traces of Mars's former magnetic field embedded in iron-rich sediments. However, none of these theories could explain the consistent geometric spacing and electromagnetic behavior of the formations. While Earth has examples of the geometric natural structures, such as the Giant's Causeway or crystalline fault veins, these are local and variable. In contrast, the Martian structures demonstrate geometric precision and continuity across thousands of miles. Some scientists have noted their resemblance to hypothetical, planetary-scale environmental control systems. Though highly speculative, the regularity and conductivity of these structures raise provocative questions. Despite cautioning against premature conclusions, NASA is taking the discovery seriously. A new mission phase is already in development. Perseverance will soon head to a site where the structures lie just 5 meters beneath the surface, close enough for more precise sampling.